Right, thank you very much. So everybody who's very attentive will see that we have 3 names on the slides. So our co-speaker Anastasia is unfortunately not able to attend today. We'll take over her part, so you're not missing out on any information. But yeah, so it's just us 2 on stage today, but we'll manage. So thank you very much for the nice introduction. So as mentioned, we will talk about a cloud-native platform for space applications today. And maybe let's start with the reasoning why, and this actually ties nicely into the last presentation we heard, because maybe you know how space missions are conducted at the moment. If you don't, it's actually everything's purpose-built. So you have purpose-built satellites running purpose-built hardware or software. And once your mission is done, basically everything is discarded. So if you have an Earth observation mission, for example, you launch your low-Earth orbit satellite, which takes a few photos, transmits them back, and basically is deorbited after this burns up in the atmosphere. Now, this is not sustainable, obviously. It's also a waste of resources and financial resources as well. So, well, you know, it's quite expensive to build a satellite, and it's also quite expensive to launch it. So we thought, why not bring cloud technology into space? Because cloud technology offers quite a few benefits which would be very good to have. For example, it enables ubiquitous access to services and data. It provides scalable and flexible computing resources, high availability and fault tolerance, which is also quite important because you just can't send a technician up to fix anything. And it is also quite a bit more cost-effective than launching your own satellites. However, it's not as easy as just running a Kubernetes on satellites and calling it a day, because there are a few challenges or limitations which we face when doing this. One is that cloud technology, obviously, because it's run on Earth, assumes continuous low latency connectivity and cannot deal with extreme latencies and disruptions. The second point is that there is no standardized execution environments for space agencies, which greatly limits adoption. And also, there is insufficient tenant separation for space hardware software platforms, which is not that nice if you want to run your experiments and your other tenant on the satellite can spy on your data. Now, how will we tackle this? Well, let's start with the biggest problem. We're doing networking in space, and this is quite a bit different from networking on Earth, because we're facing 2 main challenges. The first one is disruptions. So picture your satellite, which orbits around Earth. You have a ground station in Germany, and you want to transfer some data. As long as your satellite is somewhere over Germany, that's fine, right? You have connectivity, you can send your data, you can download data. But the satellite can't stop, so it will continue moving, and at some point, it will no longer be in range. And this is a disruption. Your download will stop, and you'll have to wait for the satellite to come back. The second problem is delays. Now, if we talk about space, we want to send data to the furthest reaches of space. But let's stay a bit more local. So if we want to send data to Mars, we're looking at an average single-trip latency of 22 minutes. So once we conclude our presentation, if we were to send a command to Mars now, it would have arrived. If we want to get a response back, we would have to wait another 22 minutes. Now, this does not play nicely with the TCP/IP stack, obviously, so we need an alternative solution. And this solution comes in the form of delay and disruption-tolerant networking, which I'm not going to go into too much detail here, but there is going to be a link on a later slide to a tech talk I held earlier this year where I explained the core concepts. Clicker does not want to click. Interesting, battery is empty apparently. Now, there we go. So for the other things in this project, multi-tenancy, as well as in cloud infrastructure in space, we have started a research project which is called DARKSOL. Now, this research project is carried out by 3 partners, we as D3TN, Cyrus Technology, and the University of Dresden, and is co-funded by the European Union and the state of Saxony. Because the topic is quite large, we split it up into 3 main research areas, which are each tackled by 1 partner. So Cyrus will take care of researching how to do a secure separation layer for multi-tenant operation. We will look into delay and disruption-tolerant application operation. And TU Dresden will build and research a delay and disruption-tolerant cloud infrastructure and the models associated with this. So this would have been the point where I would have passed the microphone to Anastasia, but you'll have to bear with me for a few more minutes, and I'll take over her part. Now, the general assumptions we've came to, well, agree on very early in the process of this research project is that we need some sort of low latency connection within a so-called space cloud cluster. Now, what we did was we discussed how to span a sort of cloud into space, and we found that it would make the most sense to separate everything into very small clusters, satellites which are in range all the time, where we have a persistent connection between the satellites, where there are no delays, where there are no disruptions, and where we can deploy Kubernetes without any problems, for example. Now, between these clusters, we can have DTN connectivity. So there can be disruptions, there can be delays, and everything can be very much more difficult to handle. We also need application execution platforms on every node in every Space Cloud cluster. And with these three assumptions, we have basically defined our Space Cloud. Very simple, right? Well, it's not that simple. We also need to take care of some requirements. So the requirements we defined are that we need to be able to flexibly distribute the platform components. We need portable, configurable, and scalable applications. We need support for multi-tenancy, as mentioned. We need to ensure that there's DTN functionality on every node and every layer. And we also need an autonomous lifecycle management to operate, adapt, and recover independently. Now, with these requirements, let's have a look at an exemplary use case. This is a very simple use case where we have an administrator and a user on Earth who are connected to a Space Cloud cluster around Mars, which consists of two satellites, Satellite A and Satellite B. There is an application running on Satellite B, which the administrator wants to, well, administrate, and the user wants to use. Now, the links between Satellite A and B are going to be consistent, which I mentioned earlier, but the links back to Earth are not going to be as stable. If we look at how this could look on the deployment side, then we have basically two users on Earth. We have the app operator and the app user, which both are connected to the application execution platform in the Space Cloud cluster using a DTN link. In the Space Cloud cluster, there are two important nodes. One is an infrastructure controller, which runs support services, such as a DNS server, NTP server, or an artifact registry. And the second one is a server node, which runs, for example, a Talos VM, which contains a Kubernetes cluster. Now, with this, is still very, very much technology tied. So what we want to do is have a model which kind of abstracts everything away, which we can use as a basis for an infrastructure. Now, this is where the MAPOS, the meta model for application execution platforms operated in space, comes into play. This is what the theorist has come up with. And this meta model has a few very nice benefits for us. So it should support the design and deployment. It is technology and distribution independent, so we can map it to different technologies. It should consider well-known technologies, such as Kubernetes. And it can integrate cross-cutting concerns, such as security features. It is also a basis for a nice infrastructure, which we can use for updates, for example, which is where Martin will take over.
Yeah, so our goal is to make satellites reusable by applying industry-standard deployment tools on satellite hardware. And based on our scenario we heard before, we want to, in example, onboard a new tenant to the space cluster. And how we do this is to spin up VMs using our multi-tenant enabled VM control plane. And how is this done? So we have the operator on Earth that needs to bundle an update package and sends this package via the DTN connection to the satellite. And the satellite then needs to process this update bundle and also to bring up the new tenant on the space cluster. So, but before we can do this, we need initial configuration of the satellite, so the base operating system, which is capable to update itself and also update the VM configuration and also to have some failure tolerance, and also a hardware reset and also AB updates, also to roll back to a previous generation if something fails. So the update bundle needs to contain, as I already mentioned, the operating system configuration, also VM images, because we are in space, so we can't have an internet connection, as Tobias already said. And also, we need an automatic dependency collection because, yeah, we want to send a bundle at once and have no possibility to get everything after the initial kickoff. Okay, and yeah, when we arrive on the satellite with this update bundle, we need to do some integrity checks and also need to see whether the configuration of the VM and also for the operating system is sane. And also, we have multiple satellites in space, so we need a zero-touch update mechanism from the initiating satellite to other satellites, and also there we need to take care of secure updates and also to roll back if something goes wrong. And we are in space, so we need a minimal operating system and also energy efficiency because we haven't that much energy there.
Right, so speaking of satellites, this is what such a Space Cloud cluster could look like. In this case, it consists of 3 satellites. One runs the control plane, including the Kube admin API server, the Kube API server. And then we have 2 worker nodes, which run kubelets and pods. And they are connected via an intra-cluster inter-satellite link, which as I mentioned earlier, is stable. So basically, this is an instance of the space cloud, right? Well, there is still a missing component because while we can, well, communicate internally in the cluster, we also need to communicate with different clusters and the applications running in these clusters. And these communications need to be delay tolerant. And this is not something Kubernetes can do out of the box. So what exactly do we need to do? Well, we need to build an application. Luckily, this does not need to be delay-tolerant communications. We just need a delay-tolerant project manager for that. We need to deploy it to a cluster. We need to send application data to other clusters. And we need to receive data from other clusters. Now, these three steps need to be delay-tolerant. So how do we, well, tackle this? Well, starting with the deployment, brief excursus, we're using Helm. Helm is a Kubernetes package manager, which uses charts. And these charts are reusable version templates for deployment, which makes it easy to upgrade, rollback, or do release tracking. And the very nice thing about Helm is that it is easily extendable through so-called plugins. So what we did was build a plugin. So there is now a helm dtn install command, which invokes Helm. Helm collects all the dependencies, all the charts that are needed, packs them into a tar, sends them to micro-DTN, which is our DTN protocol implementation, which can then, in turn, send it over a delayed or disrupted link to another micro-DTN instance in the space cluster. Now, in this micro-DTN instance, forwards it to an application lifecycle management controller, which unpacks the tar, sends the images to a local registry, and invokes Helm to deploy the pod. So we now have an application running in the space cluster, but it is still not able to communicate out of this cluster. What do we do here? Well, we're using Kubernetes, so what can we do? Well, we can use custom resource definitions. And this is where our D-gate, or DARKSOL gateway, comes into play, which acts as a tunnel between a micro-DTN instance running in the cluster and applications deployed to it. Now, the D-gate uses the application agent protocol, which is part of micro-DTN, to register agents for applications. It can register a single application, a single agent for an application, or an arbitrary number of agents. It can also register an arbitrary number of applications. What happens now is that whenever micro-DTN receives data addressed to one of these agents, it will forward it to the D-gate, which in turn will forward it to the right application. The application can process it and send data back using the same link, which will then also be forwarded to micro-DTN and sent out over the network. Now on this slide, you'll also find a link to the recording of the tech talk I mentioned earlier, where I go into a bit more details about the concepts. This was Tech Talk 26. You can also search it up on the ALASCA YouTube channel. So at the end, let's recap what we did, what we are doing, and the next step, what will be done. So DARKSOL is a research project which aims to research how to bring benefits of cloud technology to space while addressing challenges found in these environments. The goal is to research how to realize secure multi-tenant application deployments and updates on reusable satellite hardware. There has been some work done, so the next steps is basically implementation of missing components by the partners. Then we want to integrate them into a prototype and test this prototype to see if our steps we took worked and everything is usable in space. If you're interested, want to know more, feel free to ask any questions now. You can also reach out under the email addresses specified on this slide. I'll also be here tomorrow, so feel free to talk to me if you have any questions. Thank you very much.